This meeting is now being recorded.
Hello, good afternoon everyone, and welcome to this webinar on hydrogen production using solar energy. I'm Anna Hankin. I'm a postdoctoral research associate in the Electrochemical Engineering Research Group at Imperial College. This group is headed by Professor Jeff Kelsall, who is also online with me now. So the slides that I will use in the webinar are numbered. So as I go through them, please feel free to type out any emerging questions in the chat box to your left of your screens, and please also indicate the number of the slide that inspired the question so that I could refer to it later in my answers. I also recommend the use of the full screen button, which is on the top right of your screen, as otherwise a couple of diagrams may appear a little bit illegible. So the principal aim of the webinar is to highlight the concepts of using solar energy to produce hydrogen for energy storage in the UK. The storage of energy in hydrogen bonds is attractive essentially because the combustion of hydrogen produces only water. And so, unlike the combustion of carbon-based fossil fuels, which produces the greenhouse gases CO2 and I understand from the notes in the public chat that my presentation isn't audible to everybody. However, I'm getting some comments that some people can hear me, so I will continue with my talk. So as I was saying, so unlike the combustion of carbon-based fossil fuels, which produces the greenhouse gases CO2 and NOx, the combustion of hydrogen can essentially be termed a zero emissions process. But the use of hydrogen for energy storage is only really justifiable if the hydrogen is produced renewably in the first instance. So in this webinar, I will discuss two systems in which hydrogen may be produced renewably from solar energy. And the first system is the water electrolyser that is powered by electricity generated in a photovoltaic device. And the second is a photoelectrochemical reactor. So this particular comparative study is motivated by the fact that, on the one hand, it is perfectly possible to generate hydrogen from solar energy today using the first system, so the PV-powered electrolyser, because the technologies for doing so have already been developed. So one could collect solar energy using photovoltaic panels, and then the electrical energy that is generated in the panels could be used to power conventional electrolyzers in which water is split into hydrogen and oxygen. But despite the fact that the technology is there is a great amount of research taking place around the world into materials and engineering aspects of another system, and that is the photoelectrochemical reactor. So it is this work that has motivated the comparative study that I'm going to present. And the tasks that I have set out are to understand the difference between the two systems, to determine which can perform better, and to ultimately assess whether either of them are a viable solution to the energy storage problem. So I will begin, first of all, by addressing the question of why are we so determined to make hydrogen? So, well, the UK is expected to make a certain response to the climate change challenge. So firstly, by 2020, greenhouse gas emissions must be reduced by 20%. And also, 20% of energy consumption has to be supplied from renewable sources. There's also the target to electrify the heat and transport sectors by around 2030. And finally, the CO2 emissions have to be reduced by 80% by 2050. But the statistics for the current routes of electricity production by countries that are a part of the Organization for Economic Cooperation and Development show that we still have some way to go before these targets are met. Now, principally, the production of hydrogen is of great interest because it is an energy carrier that can be used to store energy efficiently, and so it can be used to directly store energy captured from fluctuating renewable sources, such as wind and solar, and this energy can then be efficiently converted back to electricity, for example, in fuel cells, which is very useful when we consider another one of the technological objectives, which is the need to smooth the dynamics of electrical power demand. So of these listed technological objectives, I will focus on the importance of hydrogen for the eventual decarbonization of road transport, which is already manifesting in the gradual emergence of hydrogen-powered vehicles and a hydrogen refueling network. So in principle, hydrogen could be generated using solar energy at refueling sites. So the idea of using hydrogen as a transport fuel is not new. I will read an extract from a book entitled Advances in Hydrogen Production, Storage and Distribution, published last summer, which says that 10 years ago, it appeared that water electrolysis and the overall production of hydrogen could undergo a major expansion because introducing hydrogen-powered fuel cell electric vehicles, FCVs, is a goal of major automobile manufacturers worldwide. And water electrolysis, powered by renewable energy, could provide the hydrogen for such a vehicle fleet, thus achieving an environmentally friendly and sustainable transportation system. But this goal seems further away today than it did 10 years ago, and mainly due to economic downturns and cutbacks in government and private sector funding for a move to a hydrogen economy. Now, however, it's evident that progress has not slowed down completely because we now see many leading car manufacturers introducing the so-called hydrogen fuel cell vehicles, of which I show several examples here. So these vehicles have great potential because they essentially offer a similar driving range to that of conventional fossil fuel-powered vehicles. So every hydrogen FCEV has a hydrogen tank, which contains several kilograms of hydrogen at high pressure, typically about 350 or 700 bar. And when required, the hydrogen is passed through a fuel cell system where it is converted to electricity by an electrochemical reaction. So hydrogen fuel cell vehicles are widely referred to as zero emissions vehicles because the only emission from the tailpipe is water. However, such vehicles will only be truly beneficial to the environment if the hydrogen fuel is also produced by an environmentally benign process. But let's look at how hydrogen is being produced at present. The statistics show that, in fact, most of the hydrogen today comes from fossil fuels, with the principal production method being the steam reforming of natural gas, in which CO2 is produced as the byproduct, so that's not a good thing. So what is considered a suitable replacement for fossil fuels as a source of energy is solar energy. Solar energy represents by far the largest of the presently useful renewable energy flows, and in contrast to other renewable energy options, there's more than enough solar energy available to permit the shift from fossil fuels. So moving on to what are the options with the existing and emerging technologies. Well, at the moment, there are three ways in which the electrical energy generated from solar energy could be utilized. So firstly, the electricity that is generated can be used to directly power electrical appliances. In this case, the energy conversion process is essentially instantaneous and there is no energy storage. Now, the second way is to charge a battery, which could later be used to power an appliance or an electrical vehicle. However, batteries are quite expensive They have finite lifetimes as well, but although research is ongoing to improve on both of these. And finally, the electrical energy could be converted into a fuel, such as hydrogen. And to do this, we could use an electrolyser, which splits water into its constituents, hydrogen and oxygen. So the hydrogen product is collected and stored, and when conventional sources of power are unable to respond to the power demand, for example, this hydrogen could be converted back to electricity in a fuel cell. So we know that this sequence of energy conversion processes works in practice. I recently saw this little demonstration model, which very effectively shows the successful capture of solar energy by a photovoltaic panel, which is on the left, and then the conversion of solar energy into oxygen and hydrogen in an electrolyzer, the transfer of the oxygen and hydrogen into a fuel cell, and reconversion of the energy stored in hydrogen back into electrical energy that drives the little propeller on the right. So this little model demonstrates how sufficient mechanical energy can be derived solely from solar energy, even after these 4 energy conversion steps. So, the first of the 2 systems that I will be examining today is the PV coupled to electrolyzer system for solar water splitting, and the processes that take place in the system are as follows. So first of all, solar photons impinge on a photovoltaic device. Now this is comprised of semiconductor layers which enable the conversion of photon energy to electrical energy, and so that an electrical current can be extracted. This electrical current could then power an electrolyzer, which is an electrochemical reactor in which water is split into hydrogen and oxygen. So the hydrogen-oxygen gas flows are then separated, and the hydrogen is stored. And subsequently, when demand arises, the hydrogen could be used in a fuel cell for electrical energy generation and for powering various appliances or vehicles. So in this case, we have 2 main components to consider, which is the photovoltaic and the electrolyzer. And I will now look at these in turn. So photovoltaic systems are typically sold and deployed in modules, which you probably would have seen at some point, and these are approximately 1 meter wide and just over 1.5 meters long. So the modules comprise multiple solar cells, little solar cells, that are coupled together to give the most efficient electrical output when the module is irradiated. And then these modules could be deployed either individually, for instance on rooftops or in gardens, or when a scaled-up system is required, they may be coupled into arrays of varying sizes. So we know that electricity is produced when light falls onto such PV systems. But as no energy conversion system is ever 100% efficient, we cannot expect that all of the energy that is carried by photons impinging on the photovoltaic panels, that it will be converted to electrical energy. There are some limitations. To begin with, there are 3 principal processes that take place inside a photovoltaic device, and each one contributes towards the penalty suffered by the efficiency of the energy conversion process. So in the first instance, the photons landing on the device have to be absorbed by the semiconductor material from which the device is made. Now the photons comes from the sun, and they carry a spectrum of energies, and the proportion of photons that is absorbed by the semiconductor is determined by its band gap, which is the minimum amount of energy that is required to excite an electron and to generate an electrical current. So a semiconductor will absorb any impinging photons that have an energy equal to or greater than its band gap. And this means that the smaller the semiconductor band gap, the more photons it will absorb, and the larger the electrical current will be, in principle. So for example, silicon has a band gap of approximately 1.1 electron volts. And so, as we can see from this graph, they can in principle absorb over 70% of the solar photons that impinge on it. Now, the second process is the spatial separation of the electrical charges that are generated when a photon has been absorbed. And when this process is slow, a process called recombination takes place, and as a result of this process, the photo-generated electrons are essentially lost. And finally, the electrical charge has to be extracted from the PV device in order to be useful, and some losses occur at this stage as well. So hence, in the end, A typical commercial silicon PV module will have an efficiency between 13 and 18% or thereabouts. And there's a great deal of ongoing research into photovoltaic materials, device structures, and fabrication methods, which have given rise to cells with efficiencies as high as 44.7%. But the composition and fabrication methods for such cells render them prohibitively expensive for widespread commercial deployment at the moment. So the efficiency of a photovoltaic device, whether it's a single cell or a whole module, is computed as the ratio between the electrical power output and the solar power input. Now, the electrical power output is determined from the voltage across the illuminated device and the current that the device generates. And these values depend very much on the structure of the device and the materials from which it is made. And the solar power input is a function of solar irradiance and the size of the device area over which the photons are captured. And the irradiance, of course, depends on the geographic coordinates and also on the weather at the time of measurement. Now, also, the efficiencies, which are provided by PV module manufacturers, are recorded under highly controlled conditions of 25 degrees C and direct radiation by the 1.5 AM solar spectrum. But typically, the real temperature of an irradiated PV module differs from 25 degrees C, and so it tends to perform less well than under ideal testing conditions. And in addition to that, most of the time, photons do not impinge on the surface of the PV at 90 degrees, and this results in an additional decrease in performance compared to manufacturer specifications. The estimates suggest that additional losses of approximately 23% may be expected, and hence the low module efficiencies of 13 to 18% mentioned earlier will suffer even further. And finally, when multiple modules are coupled together, the overall system suffers from efficiency losses due to resistance in cables and inverters and transformers and so on, and that will also have an impact. So, to demonstrate the effective efficiency on the collection of solar energy, if we are considering setting up a PV system in London, UK, in order to power some electrolyzers for hydrogen production, the average daily amounts of energy that could be obtained per square meter covered by commercial PV modules are shown in the slide. So the green bars show the actual solar irradiance or insolation. The orange bars show the amount of electrical energy that could be extracted by a photovoltaic module with a peak power output of 15%, with a 15% efficiency. So then finally, the blue bars show the most realistic electrical energy output if further losses due to temperature changes, etc., is taken into account. But essentially, what do these numbers really mean? So in order to understand whether these numbers are high or whether they're low, we need to know how much energy is actually required to operate electrolyzers, and also, of course, how much hydrogen these electrolyzers would ideally need to produce at a particular location. So before we can do that, we need to look at the requirements of the electrolyzer system to which they will be coupled. There exist several types of electrolyzers, all of which can, in principle, be powered by PV. So first we have an alkaline electrolyzer, and as the name suggests, it operates with an aqueous alkaline electrolyte, such as potassium hydroxide. There's also a polymer electrolyte membrane electrolyzer, which operates with an acidic electrolyte, and this one is able to operate at higher current densities than the alkaline electrolyzer, but this is more expensive because the corrosive acidic environment demands the use of noble metal electrodes. There's an additional class of electrolyzers which is under development at present, and that is the solid oxide electrolyzer. So unlike the other two electrolyzers, this one operates with steam rather than with liquid water, and the advantage of this is that the thermodynamic requirements for the reduction of steam to hydrogen are more favorable than the reduction of water to hydrogen. So the solid oxide structures are still currently susceptible to degradation and failure, and so this class of electrolyzers has not yet actually gone into widespread use. So I'll briefly cover the processes that take place in the electrolyzers. Despite the differences that I've just highlighted between the systems, the fundamental processes taking place during operation of all three of them are essentially the same. So all electrolyzers have two electrodes, which are shown here in blue and red, and is separated by an electrolyte, shown in green. So the electrodes are electronic conductors, and the electrolyte is an ionic conductor. And during operation, a voltage applied between the electrodes triggers a flow of current, which supports electrochemical reactions taking place at the interface between each electrode and the electrolyte. So broadly speaking, the negatively polarized electrode is known as the cathode, shown here in blue, and it supports reduction processes, while the positively polarized electrode, as shown in red, is known as the anode, and it supports oxidation processes. And the two electrons are often also separated by a membrane that prevents the mixing of the reaction products at the two electrodes. So during a reduction process at the interface between a negatively charged cathode and the electrolyte, the electrons, which are indicated in this diagram with an E-, cross the interphasial boundary from the cathode and give rise to a chemical change in the species in the electrolyte. So for instance, in an alkaline electrolyzer, electrons reduce water at the interface to hydrogen and hydroxide ions. The hydroxide ions then carry the current in the electrolyte by migrating to the positively charged anode. And at the anode, chemical species are stripped of electrons, which cross the interphasial boundary and into the electrode. So these hydroxide ions would be oxidized to oxygen and water. But ultimately, what we're really interested in is, of course, is the rate at which hydrogen can be produced in these devices and how much power input is required in order to achieve that. So the current that flows through the device, divided by the area of the electrode, gives the current density. And the current density is a direct measure of the rate of the reaction, and this is known as Faraday's law of electrolysis. So the higher the current density, the faster the reaction is taking place, and the more products, such as hydrogen, could be harvested per unit time. But how do we predict the kinetics of the process, or how do we predict the rate at which the reaction will happen? Well, this is directly related to the thermodynamics. So the overall water splitting process is endothermic, as you probably know, which means that energy must be added to drive the reaction. And so to start off with, what is usually computed is the equilibrium potential for any given overall process in an electrochemical reactor. And this equilibrium potential tells us the minimum voltage that must be applied to drive the process. So the computed equilibrium potential for a process may vary a little bit depending on whether it's calculated from the standard enthalpy, shown here as delta H, or Gibbs free energy, delta G, and it will also vary with things like temperature at which the process is taking place, as well as the physical state of the reactants and products, which could be liquid or gaseous, for example. And the consensus that it doesn't really matter which thermodynamic quantities are used to calculate the equilibrium potential, provided they are specified clearly. But now, if the precise value of the equilibrium potential is applied between the electrodes, the equilibrium will just be maintained, and the rate of the reactions at both electrodes of the electrolyzer will be completely negligible. So hence, a higher voltage than the equilibrium value will need to be applied to get an appreciable current to flow. And the voltage required to achieve a particular current, it depends on the type of electrolyte and on electrode materials. So just as an example here in this graph, I show a performance curve for an arbitrary alkaline electrolyzer operating with a nickel cathode and a nickel anode, and it demonstrates that the current density increases exponentially as the applied cell voltage is increased above the equilibrium value, which is great, but an electrolyzer is an energy conversion system just like a PV device, and hence it carries its own efficiency limitation. So the efficiency of an electrolyzer is computed based on the ratio between the equilibrium potential and the actual applied cell potential. And it is also affected by the charge yield of the principal reaction, which refers to cases when, for example, several reactions are taking place in parallel on the same electrode, meaning that only a fraction of the overall current density is actually contributing to the formation of the desired product. And the second graph, the graph on the bottom here in red, shows the dependence of the charge yield for water reduction to hydrogen on the current density. and so it increases to unity with increasing current density. The final noteworthy parameter, which is usually provided in the electrolyzer specifications by the manufacturer, is a specific electrical energy consumption of the electrolyzer. And this specifies the energy demand for producing a particular quantity of product at the chosen operating conditions. And it quite clearly highlights the cost penalty of increasing the operating voltage and current density of the electrolyzer. So, finally, I'd like to comment on how the performance of the combined PV plus electrolyzer system is characterized. So the operating conditions of the combined system are determined by comparing the performance curves of the individual PV and electrolyzer systems, which are graphs of current versus voltage. And in order for one system to power the other, the operating voltages and currents, of course, have to match. So when the two systems are coupled, the overall efficiency with which the solar energy is converted to chemical energy, so hydrogen, for example, is computed by multiplying the individual efficiencies of the two systems and also by the coupling factor, which is calculated as the ratio of the PV power achieved and the maximum PV power that could be achieved at peak performance. So just to recap on this system before we move on to looking at the photoelectrochemical system, so in order to evaluate the performance of a PV plus electrolyzer system, the two components have to be characterized separately. And this will enable the determination of the coupling factor and operating conditions for the combined performance. So now, let us look at the alternative system that's being developed worldwide for converting solar energy to chemical energy in the form of hydrogen. So in this case, rather than having two separate devices, one for converting solar to electrical energy and another for converting electrical energy to chemical energy, there is an option to have just one single device, it's called the photoelectrochemical reactor, in which both of the energy conversion processes take place. So such a device is essentially an electrochemical reactor, but with photosensitive electrodes that can perform the same function as a PV, so the absorption of photons. So hence it's called the photoelectrochemical reactor, or alternatively photoelectrochemical cell, now commonly abbreviated as PEC. And the main idea behind this two-in-one device is that it eliminates the need for cables and long transportation routes for electrons from the PV system to the electrolyzer system. So the transportation length is decreased from many, many meters to several millimeters or even nanometers, depending on how the device is constructed. And this can potentially really increase the hydrogen generation efficiency and rate. And I think I should mention that another name for such a system, which is becoming very commonplace and you've possibly heard of, is an artificial leaf, or the process, overall process in this reactor is referred to as artificial photosynthesis. So those are very much the same thing. So there are certain considerations which must be addressed in the design of a photoelectrochemical reactor that are either not necessary or have already been addressed for a PV plus electrolyzer system. So firstly, there's the question of materials that must be addressed. There are many issues here to do with material compatibilities, stability, and also how they will be sealed inside the reactors. There's then the question of the construction of the reactor body, the materials, and the geometry. The geometry in particular is very important and very much dictated by the way in which the reactor is illuminated. So it's easy to illuminate a PV, but not so with the photoelectrochemical reactor. And to determine the illumination mode, we have to consider whether both sides of the reactor require illumination. For example, will light be directed towards the electrodes using mirrors or some other optical component? We have to think about whether a membrane is necessary to separate the reaction products. Is it essential or does it complicate the design? Is an external bias required? Also, how will the electrolyte be distributed or pumped? And how big a flow network is required? And finally, how will the products be harvested and stored? So I'll come back to these issues once I've introduced some examples of them. Just to comment on the efficiency, so the efficiency of this system is computed as the ratio of the amount of chemical energy produced. So for example, the energy is stored in hydrogen bonds, to the amount of solar energy input within a time period. So we've already seen the calculation for the solar energy input. It's the incident solar power density multiplied by the photoactive area. And the chemical energy produced is computed as the rate of hydrogen evolution multiplied by the Gibbs free energy of hydrogen formation. And I should note that the solar to hydrogen efficiency calculation is only really applicable to photoelectrochemical devices that are powered by solar energy only and not by any additional externally applied bias. So this calculation is notably more laborious than the characterization of the PV plus electrolyser system, but it is necessary in order to prevent any corrosion of poorly characterized chemically unstable electrodes from influencing the efficiency, which could otherwise be calculated as current by voltage as before. But so, coming back to my main question, so if PVs and electrolyzers are already readily available, then why are research and working on the combined system? It's clearly more tricky. So to answer these questions, I'll now put forward several case studies in which I will try and assess whether, if we were to take some readily available PV and electrolyzer systems and couple them, we could produce sufficient quantities of hydrogen to meet an industrial application. And my industrial application of choice is the refueling of a hydrogen fuel cell vehicle. And I will first show a case study conducted by General Motors in Milton, Michigan, United States. And I will then present several of my own case studies, both for industrial scale refueling and home refueling. So, this is a proof of concept study conducted by General Motors in 2011. And this study firstly involved 4 photovoltaic arrays with 10 modules in each one. So essentially 40 PV modules were used in total, with each one able to deliver a peak power output of 590 watts. So this PV system was coupled to a custom-built electrolyzer operating with an alkaline potassium hydroxide electrolyte. And this electrolyzer was able to generate hydrogen gas with very high purity, 99.999%, at an output pressure of 138 bar. And finally, the hydrogen produced by the system was used to refuel a Chevrolet fuel cell Equinox vehicle. So the study evaluated the mean operating efficiency of the PV array to be about 13.7%. The alkaline electrolyzer operated with an efficiency of 59%, and the mean system coupling factor was 91%. So, the overall efficiency for the conversion of solar energy to hydrogen was 8.2%. And the performance of the whole PV plus electrolyzer system was monitored over 109 days. And the solar insolation, of course, varied substantially over these 109 days. So there's a record of the mass of hydrogen generated for different levels of insolation. And the gradient of the linear regression line fitted to the data shows that 0.1 kilogram of hydrogen was generated by the system per kilowatt hour of solar insolation per meter squared. So if this number is normalized by the number of PV modules used, we obtain a hydrogen generation rate of 2.5 grams of hydrogen per module per day per unit of solar insolation, which doesn't sound like a lot. So the average solar insolation in Michigan is actually 4.2 kilowatt hours per meter squared per day, and the UK average is about 3.3 kilowatt hours per meter squared per day. So in order to identify the hydrogen production rate that is actually required of a particular system, so simply because 2.5 grams of hydrogen per day doesn't sound like a lot, but we need to look at a UK-based case study, and I will do this for a refueling station to see if it's feasible to support a refueling station with solar energy alone. So, because it could potentially be a very interesting demonstration project. And currently, there are very few hydrogen refueling stations in the UK. However, the numbers are projected to increase, as evidenced from the vision of the UK H2 mobility project. But that's in the future, and what we have now is this. So this is a map of the existing hydrogen refueling stations in England and Wales. And some of these stations service cars and buses, some of them service cars only. Some stations refill vehicle tanks at a range of pressures. Some service vehicles at one pressure only. Some stations are only accessible by appointment and others are open all the time. But essentially, the absence of a great number of stations creates an opportunity for doing a demonstration project for producing hydrogen for refueling purposes with solar energy only. So to do a case study in order to identify the requirements for such a station, we select the BOC Honda hydrogen refueling station in Swindon. So this refueling station is designed to enable the refueling of hydrogen fuel cell vehicles at a rate of approximately 4 vehicles per hour. So in this case study, we'll focus on cars rather than buses. And the car with the largest tank capacity from the flashy cars that we looked at on an earlier slide was the Hyundai iX35. And this has a tank capacity of 5.6 kilograms. So we should assume that the station should enable the refueling of 4 vehicles with tanks of this size per hour. So then if we take the peak operating hours of a refueling station as being between 7 a.m. and 8 p.m., for example, so a total of 13 hours, we can estimate that a typical station will be required to provide 290 kilograms of hydrogen per day. So now in terms of the kind of electrolyzer that could be used to generate the hydrogen, we can use the example of a hydrogenics electrolyser, which has been designed specifically for hydrogen vehicle refueling purposes. So I have some figures here for the specific electrical energy consumption of hydrogen production in this electrolyser for both operating pressures. And if we take the higher figure for the higher refueling pressure, we can estimate that a total of 19,720 kilowatt hours of energy is required by the Swindon station for the electrolytic production of its hydrogen. So now, how many PV modules would it take to provide this hydrogen? So to make this calculation, I will use some information provided by a company called Conergy about their solar park in Hampshire. So if we take the average solar installation throughout the year in Swindon, which is essentially the same as it is in London, which is 3.5 kilowatt hours per meter squared per day, and multiply it by the specified Conergy module efficiency, and then finally corrected by the 23% loss that is expected based on temperature fluctuations, we can expect that an array of Conergy PV modules will generate approximately 0.4 kilowatt hours of energy per meter squared per day. So this means that approximately 30,000 PV modules are required to fulfill the daily requirements of the Swindon refueling station. And if we include the walking space required for PV maintenance, we can compute that the total amount of space required for these PV installations for supporting the station is approximately 0.07 square kilometers, which is roughly 265 meters by 265 meters. So whether this is an acceptable size for every refueling station, of course, depends on the location for the station. But it seems to be a sufficiently small size to permit a demonstration project, for example. But of course, this estimation doesn't take into account the coupling factor because we don't actually know the performance curves for the solar farm or for the electrolyzer. So what we've actually calculated is probably the best case scenario. So is it feasible for every hydrogen station to require this much space or not? I'll now present a slightly different case study because in reality we might expect to see people refueling at home. So let's see if that looks like it will work. We know that it's possible to recharge an electric car at home, so it's sensible to also see whether it would be possible to refuel an FCEV at home by powering an electrolyzer with a rooftop PV system. So then if we take a PV system of the maximum size that's permissible in the UK for any household, which is 4 kilowatts,
Apologies, everybody. We seem to have lost Anna just there for a moment. Please bear with us a second to get Anna back online with the audience. Apologies, everybody. We still seem to have some technical issues here with the sound. Please bear with us a couple of more minutes, and I hope to get everything back on track then.
Hello? Hello, everyone. I believe that I was cut off at some point during the presentation. So if everyone can hear me again, could someone please let me know at which point I got cut off so I can resume my talk from the appropriate point?
Hey, hello, Anna. I can hear you well again now. I think it was the previous slide where you got cut off. Or
So the previous slide with the electrical cars.
I stand corrected. If you look at Julian's K houses chat there.
3 slides.
So maybe a few slides earlier.
Okay.
Yes.
Slide 38. Oh, wow. Oh, okay. So by the end of the slide, I had computed the amount of so the size, essentially the size of the field that one would need to populate with PV modules in order to be able to support a typical commercial hydrogen refueling station such as the one in Swindon. So my calculation there showed that in order to support such a station, you would need approximately 30,000 PV modules and a field of the size of approximately 265 meters by 265 meters. And I sort of mused over the concept of whether this was a very large field or not to cover with PVs, if that's what you needed to do for every single refueling station. So the conclusion is that it's probably quite a massive amount of space that is required, and that it would not be appropriate for every refueling station. But I concluded that it's a small enough amount of space to perhaps enable a demonstration project. And then I went on to saying, so perhaps it's difficult to judge whether this is a large requirement on space or not, and that we should consider a case study with a home refueling system. So we know the size of a PV system that one is permitted to have at home, which is a 4 kilowatt system. And so I was calculating how much hydrogen you could generate per year and how many times you might be able to refuel a car. So if we take a PV system of the maximum size that's permissible in the UK, so 4 kilowatt hours, well, we know that, for example, if this was in London or in Swindon, the daily energy production is about 10.8 kilowatt hours. So if we again use the specific electrical energy consumption of the Hydrogenics high-pressure alkaline electrolyzer of 68 kilowatt hours per kilogram of hydrogen, we can compute the amount of time that would be required for generating enough hydrogen to refuel a car with a tank of 5.6 kilograms. And we find that such a car can be refilled roughly only 10 times a year, and it would take several months of hydrogen generation in winter to just refill a car once. And on average, you may be able to travel just over 6,000 kilometers. So an obvious comparison at this point would be of the performance of an FCEV with the performance of an electrical vehicle. And here are several notable electrical vehicle models for which I have computed the annual travel distance based on the amount of energy that could be provided by the 4 kilowatt rooftop PV system we considered in the previous slide. So calculations show that an electrical vehicle powered by a PV system will travel considerably further than a hydrogen fuel cell vehicle powered by the same PV system. And so what this is essentially suggesting is that at present, renewable energy storage in batteries is more favorable than renewable energy storage in hydrogen. So the limitation is evidently imposed by the electrolyzer because the specific electrical energy consumption per kilogram of hydrogen is just simply too high. So what options have we got? Well, we could consider using a different type of electrolyzer. So I mentioned earlier that the solid oxide class of electrolyzer is currently under development, but these electrolyzers are fabricated very differently to the aqueous electrolyzers and look very different as a result. So this is a sketch of a microtubular solid oxide electrolyzer. So as an individual reactor, it's very small. So multiple electrolyzers need to be stacked in order to generate substantial quantities of hydrogen. But the main advantage is that the electrodes are porous. and the density of the electrode-electrolyte interface is very high, and this creates a high reaction surface area per unit volume taken up by the cell. And so these systems can, in principle, generate hydrogen at much higher volumetric current densities than the aqueous system. And this is also facilitated by the gaseous nature of the reactors and the excellent kinetics at high operating temperatures. The specific electrical energy consumption of such systems is approximately half of that required by the hydrogenic electrolyzer that I considered in the earlier calculations. However, so firstly, the specific electrical energy consumption of figure of 37.5 kilowatt hours per kilogram of hydrogen, it doesn't take into account the energy required to maintain the high temperature that's necessary for the reaction to take place. And secondly, the calculations refer to gases at atmospheric pressure rather than at the elevated pressure required for hydrogen refueling, hydrogen vehicle refueling, so with which the hydrogenic electrolyte does. But even if the specific electrical energy consumption of these electrolyzers was indeed half that of the aqueous system, it still wouldn't be enough to make FCV refueling more favorable than the recharging of batteries for energy storage. So just to summarize the findings for the PV plus electrolyzer arrangement, in terms of the advantages, we have the fact that two systems that need to be coupled together in order to generate hydrogen from solar energy are already readily available, and coupling them does not require any major additional effort. So a study will, of course, be required in order to characterize the combined efficiency of operation of any two chosen systems, and this will depend on the size of the PV array and the modules used, and also on the electrolyzer system. But one big disadvantage of coupling two separate systems will be in the losses associated with the flux of electrical current from PV array to electrolyzers, which is subject to resistive losses. And finally, the fact that the specific electrical energy consumption of electrolyzers is too high, it renders them less favorable than batteries for energy storage. However, I really should note that the capital cost and serviceability of electrolyzers versus batteries has not been assessed in this particular study, and that such a comparison may very well render electrolyzers more favorable. So now I would like to move on to discussing photoelectrochemical systems. And I will comment on how they are structured, the performance that they demonstrate, and some of their advantages and disadvantages. So, one of the early studies of such a system was conducted by Patilif and Turner at the National Renewable Energy Laboratory in the United States, and it utilized a monolithic multiple junction solar cell as one of the electrodes in an electrolyzer. So what they in fact did was take a multiple junction PV cell of the type that is leading the PV efficiency table at the moment and immerse it in the electrolyte such that all of the electrical charge generated upon illumination would be transferred instantaneously, almost instantaneously, across the electrode-electrolyte interface. And this photoelectrode was used to enhance the oxygen evolution current in the system. Now, this device was illuminated from one side only, but with very intense light, measuring its 11 suns. And so, in other words, the intensity of the light was 11 times greater than that reaching the Earth's surface from the sun in the normal conditions. So, at this intensity, they obtained a current density of 1.2 kiloamps per meter squared. So now we can estimate what the investigators would have achieved in the absence of intensified illumination. So, at one sun, they would have achieved 90 amps per square meter, and from Faraday's law, we can conclude that the rate of hydrogen production in this system would be 13 grams per day per meter squared of photoabsorber area. So the solar to hydrogen conversion efficiency of 12.4% obtained by the investigators is actually quite substantial, and indeed it's higher than the one measured by General Motors in their system, so which is excellent. But it should be noted that the solar to hydrogen conversion efficiency here applies to a small device designed for laboratory scale experiments, and hence it remains to be seen what would happen to this efficiency once such a device is scaled up. So another study performed by the research group of Professor Dan Nacera, who's now based at Harvard, it employed a silicon-based multi-junction cell as the photoabsorber, and they tested it in 2 different device configurations in order to see the effect of device configuration and geometry on the overall performance and, most importantly, on the solar to hydrogen conversion efficiency. So in the first instance, they tried a monolithic device structure in which all of the layers of the photoelectrolyser were deposited one on top of the other. So thereby they minimized the resistance to electronic current flow between the electrodes, because such a device actually doesn't need any kind of external circuit at all. But in such a setup, they obtained an overall solar to hydrogen conversion efficiency of only 1.7%. Now, this low figure is attributed to the non-uniform pathway for the ionic current that had to go around from one electrode to the other. And this is essentially because of the electrode configuration. But in the second configuration, where they had the electroactive faces of both the photoanode and the cathode facing each other, the ionic current distribution was more uniform. But it made the illumination of the triple junction solar cell more tricky. It was made possible by using mesh materials for the cathode so that light could pass through the cathode and illuminate the photoactive component. And in this configuration, they achieved a solar to hydrogen conversion efficiency of 4.7%. But essentially, this work highlights the great importance of engineering on the performance of a photoelectrochemical system, because performance is not only a function of materials and their ability to absorb light, or even to catalyze electrochemical processes, but it is also highly dependent on geometry of the reactor design, which affects the uniformity of current and voltage distribution and how the device should be illuminated. So these structures are very complex indeed. So one last example of a photoelectrochemical device design that I'd like to show was produced by a team at Uppsala University, and it's based on a semiconductor known as SIGS, which is made from copper, indium, gallium, and selenide. But despite comprising expensive elements, this material has a higher absorption coefficient than that of silicon, and so it's actually now beginning to compete with silicon as a material for solar panel production, I believe. So in the device presented here on this slide, 3 individual SIG cells with a combined PV efficiency of 17% are coupled together to drive water splitting at 2 platinum electrodes. But the problem is SIGS is not stable in aqueous solution, and so it actually had to be protected with various transparent polymers prior to immersion. But still, the overall solar to hydrogen conversion efficiency was 10%. Which is again higher than that achieved in the General Motors study. But once again, it's applicable only really to a small device. So, from the 3 examples presented above, we can see that the solar to hydrogen conversion efficiencies of photoelectrochemical systems are at least on par and potentially even better than those of the coupled PV and electrolyzer systems. So this, of course, suggests that ongoing research into photoelectrochemical systems and the materials and the reactor designs is very, very much worthwhile. But there's no denying that research is taking quite a long time. And the question is why? So the main problem is that more often than not, a good photoabsorber will not be stable in aqueous solution. So this means that even if an absorber functions very well as an externally mounted PV, there may be severe complications upon its immersion into solution. And in addition to that, it may also be a poor catalyst for the required electrochemical process. And both of these problems often mean that the photoabsorber requires special coatings to simultaneously protect it from dissolution and catalyze electrochemical processes, whilst also not blocking the sunlight from reaching the absorber. So hence, there is an enormous amount of material tailoring and development involved, and this of course complicates the photoelectric fabrication process, which is why research is taking such a long time. And if we directly compare the PV plus electrolyzer and the photoelectrochemical systems, we can see that there's quite a substantial difference in the design considerations that one would need to address before deciding which one to use ultimately. So some major questions relating to the photoelectrochemical system in particular are how will it be illuminated? And if the reactor requires illumination from both sides, how is it to be done? So should the reactor be tilted so that it's illuminated at an optimum angle? How will the electrolyte flow will be distributed? So this is all quite complex in contrast to a PV. And also, if the photoabsorber is to be immersed in a liquid, will it remain stable? Will it dissolve? Does it require protective coatings? So if the PV electrolyzer system is compared with the photoelectrochemical system in terms of material stability issues, device design issues, and the amount of material involved in building the system, on the face of it, the photoelectrochemical reactor loses out because of all these extra complexities. But it doesn't follow that the photoelectrochemical system cannot be constructed in such a way that per unit area of ground space it will not produce more hydrogen, which is really why we're looking at it. So at this point I'd like to state what I see as an advantage and a potential way forward with the installation of photoelectrochemical reactors. And that's in the way that the devices are illuminated. So just to recap, the installation of the PV, as I mentioned, is a straightforward process because it could simply be tilted to any angle that is optimum for a given geographical location, and then it's connected to an electrolyzer which could stand whichever way it likes. But in a photoelectrochemical reactor, which has electrolyte flowing through it and gas outlets that should not be flooded, is not as maneuverable. And if it requires radiation from both sides, this could be a problem. But this could be achieved with mirrors, for example. So the most straightforward way is with mirrors, which would need to be positioned at 45-degree angles on either side of the reactor. This is really a space-consuming arrangement because essentially the mirrors will each take up a reactor height's worth of space, and space, as we know, is very, very valuable. And such a system is not really likely to produce more hydrogen per unit ground area than the PV plus electrolyzer system. But there is an alternative method by which the electrodes in a photoelectrochemical system could be irradiated, and this could also serve to this method could also serve to concentrate the sunlight and thereby increase the hydrogen production rate. So that is by concentrating the light by using well, there is a choice of a number of concentrators that are available industrially. And the concentrated light should serve to improve the performance of a photoelectrochemical reactor actually much better than it would if it was applied to just a PV system, because the performance of most PVs suffers with increase in temperature above 25 degrees C. And there are not many systems where the PV is being cooled, or at least that's a much more expensive process. But the photoelectrochemical reactor performance should be affected less strongly due to the cooling because of the cooling effect that's exerted by the flowing electrolyte. So hence, concentrators could, in principle, be very effective at enhancing the hydrogen production rate, and they could also be used or designed to effectively couple photoelectrochemical reactors together in such a way that could minimize the amount of ground space that is taken up per reactor. So, to conclude this webinar, so I've determined that the PV electrolyzer system, which could, in principle, already be deployed for solar hydrogen production today, has considerable advantages over the photoelectrochemical reactor system on many counts. So there's no need for protective coatings of photoabsorbers. There are fewer issues with stabilities. Certain types of losses could be obviated, and a broader range of electrolytes could be used. However, I also determined that it is not really practical to use such systems for the industrial application, and the one I considered was hydrogen for vehicle refueling. So then when I looked at photoelectrochemical reactors, they look to be notoriously more complicated than the PV plus electrolyzer systems. However, their performance is extremely promising and so far is doing better than for the PV plus electrolyser system. And hence this encourages further work in this field, which is ongoing, and more projects for device scale-up and particularly optimization of device illumination strategies, because engineering is a very important aspect in this field. So, thank you very much for listening. Jeff Kelsel, who's with me, will, I guess, go over some of the questions. And if you have to run, there's also an exit poll, I think, that will come up at the end of this webinar.
Yes, we'd be very grateful for some feedback using the exit poll. There are a few questions perhaps we should address. The first coming from Ashwati Iyer, if I pronounced his name correctly. He's asking, what material has the greatest potential to be a good photocatalyst for hydrogen production? Well, this is not a question that's easy to answer quickly, but you have to bear in mind, firstly, that any chemical reactor needs to have at least three objectives that it achieves. It needs to be efficient, cheap, and robust. And in practice, there's always some conflict between these desirable properties. But coming specifically to the photoelectrochemical system, it's often not the hydrogen production that's the main issue, but the much slower reaction involving oxygen evolution. And the need for that photoanode to be stable under the particular conditions used, particularly to dissolution. So there are a range of options which are being explored, but perhaps it's naive to believe there will be a single solution to this problem, and better to decouple the effects of photon absorption from the catalysis, in this case, of oxygen evolution. So there are a range of possibilities there, but as ever, the best catalyst tends to be a precious metal containing material, which will be more expensive. So there's likely to be a trade-off between cost and efficiency, and indeed longevity. Some of the other questions that came up during the webinar, I hope have been addressed by Anna already, but several people raised the issue as to whether there were other applications for photo-generated hydrogen, and indeed there are. So Julie Stevenson, for example, suggested quite rightly that hydrogen can be used to make liquid fuels. Most simply, the reduction of carbon dioxide with hydrogen to make methanol. But there are other possibilities. The hydrogen can also be used for grid-scale storage, as suggested by Jacqueline Edge, and indeed that's a sort of technological application on which we're working in other projects. So you can feed hydrogen or indeed methane directly into a gas distribution network. Jane Patterson suggested using hydrogen for oil refining. Hello Jane, if you're still there. And Neil Fraser mentioned chemical production, particularly the production of ammonia. So all those are possible. Are there any other questions that we've not addressed either during the webinar or subsequently? Just looking at the public chat. So nothing else coming up. So lastly, from Anna.
So thank you very much for joining this webinar. And so please also feel free to email me with any questions, and you should have my email from the initial advertisement, I guess, with any further questions that you might have.
One's just coming in from Richard, and the question is, are you looking into this research of solar to hydrogen? Very much so.
Yes, we are. So we're very much addressing converting solar energy to electrochemical energy, to electrical energy, and then to chemical energy. So we have the electro component sort of as an integral part of our research, which is why we're not looking at any other ways of making hydrogen, such as the ones that have been suggested in the chat. Yes. So we work principally on photoelectrochemical systems. They are of interest to us. Yeah.
There is one issue I perhaps should have mentioned earlier, and that's to do with photocathodes, and it's they which are particularly unstable and which probably limited the lifetime of the NREL electrolyser that Anna showed in one of her slides.
The first one, yeah.
So, lastly, thank you very much for attending. We'd be very grateful if you could fill in the online
exit poll.
Yes.
Yeah. Thank you very much.
Thanks again. Bye.
Bye.